Welcome back. So just the temperature is okay for you now? Okay, yeah. Okay, yesterday was freezing, yeah. So before we start with this lecture, let me introduce you to some books that are references that I will leave them here in the, if you want at the coffee break or whatever, you can take a look, take a photo or. So what are the references that are more close to this course would be these two books. One is called Modeling Infectious Diseases in Human and Animals by Keeling and Rouhani. That's the kind of the textbook that is used over the world, let's say. Okay? It's the kind of standard thing. There are things I like it, there are things I don't like so much, but it has a lot of things about models. But I mean, you have to know the math, okay? If you don't know the math, then. This one is it's called Mathematical Epidemiology, and it's edited by Fred Brow, Pauline van der Drische, and Yang Hong Wu. And it is made in the form of contributions of different authors. So the part of the talk of the first lecture yesterday was taken from here. So, for instance, those plots are taken from there, from this book. Okay, and that's very nice. It has compartmental models, discussion, long discussion. Then has also stochastic models, has advanced modeling also. And I will refer to this one of those chapters in the next class, not today. So these are both books that are of mathematical epidemiology. Now, maybe you could be interested in modeling more closely a certain, because this is general. Like I did SIR model, but well, I was referring to measles because that's the one of the diseases that fits some of the hypotheses. But given a disease, you may have to build other kinds of model. There's this old book that is edited by Roy Anderson from the 80s. And you may find it in, I don't know if you find it on pirate things. Yeah, maybe Anna's. And this is like, okay, directly transmitted diseases, bacterial diseases, hookworms. Then there's population dynamics of malaria. Then there is also schistosomiasis and orchocerciasis and fox rabies and other things. And this doesn't have so much math. I mean, there is math because it's modeling, but it is less focused on math and more on looking at the disease, what are the data that exist, and what is the kind of model that you should use. The same authors have a very important book, and I mean, the same author, Roy Anderson and Robert May. Robert May was one of the very important modelers I mean, he worked a lot of models for HIV/AIDS and so on. It was very important, and he's also very important in ecology. And by the way, as a physicist, you know, by training, and also was president of the Royal Society. You know. So this is also very much not so mathematical. Lots of data, discussions, and so on. Okay. And on the opposite side of this, if you really want to go for the crazy math, I mean, yeah, really wild thing, okay? I want theorems. I don't want math like physicists, okay? Because what we do here is is like a physicist, because I'm a physicist, but physicists usually look at things and they don't prove theorems, they solve equations and they try to connect with data, but maybe you would be interested in the math. So one of the books that is relatively new, less than 10 years, I think, it's one, it doesn't say, okay, but it should be less than 10 years old. So it's this book, Mathematical Models in Epidemiology, by Fred Brouwer, the same of one of the organizers of this one, and Carlos Castillo Chavez and Zilang Fink. Carlos Castillo Chavez is a very important person in mathematical biology, but on the more mathematical side. Okay? And then here you get more math, really. Okay, and this is not the thing that we do here. Okay? But if you are interested, you can take a look at this. And well, there are a lot of other books also, but my suggestion is if you want to start with some bibliography about this subject, I recommend one of those. Okay, so let's give further steps on our modeling, on the models that we are developing. So let me just briefly restate what we have done yesterday in terms of models. We have built the first model with the SIR model. Okay? There's assumptions, many assumptions, but an important assumption is that we are talking about a disease that confers lifelong immunity, or at least over the time span that we are modeling, people get immune. Okay? Yesterday, for instance, Renato told you about waning immunity, so that's a modification of SIR that takes into account that you can have partial immunity also, and so on. And so we built this model, and there are other things that are assumptions that are common to all compartmental models, which is that the population is well mixed, it's not clustered, and everybody can, in principle, get in contact with all the others. In principle, this doesn't mean it has. And well, and then what we saw that this model results in some predictions of the model, where you have the typical curves, the epidemic curves. I didn't have them here. Which look like, oops, not this one, are like this, okay? And you have the infectious increase. If there is an epidemic, the number of infections increases and then decreases. It's not symmetrical. The number of susceptibles can only decrease, and the number of recovered can only increase. Right? So, and then we looked at this, and there are other things that we actually could derive was that at the end of the epidemic, describe it by SIR model, at the end there are still susceptibles. Not everybody has been infected. Yeah? So there's a burnout of the and then we could calculate the number of susceptibles at the end of the epidemic, and which also implied that we can know the number of the total number of people that have been infected over the course of the epidemic. So, which we called the final population, the total population, total size of the epidemic. Okay, And this is an important result, okay? Because it has the implication that all of this the fact that you have an epidemic depends only on R0, which we have defined, and the total epidemic size depends also only on R0. So something which can be calculated at the very beginning gives you a result about what should happen over the whole story, whole epidemic, okay? Which gives you at least an order of magnitude of how bad can this be, okay? So, now, that was nice. We could, for instance, look for measles and try to find a model which has this has an epidemic peak and so on. It was okay. We had a problem that obviously what we were made, our developments were made for a disease, a pathogen that arrives at a population, and the population is completely susceptible. But obviously, this is not valid for measles. Measles has a long story. And actually, you have to consider, instead of at the initial point of, at the time t equal to 0, you have to consider that not all population is susceptible. There's only a fraction that is susceptible. And then there is the problem, which fraction? And this is a problem for modeling. To really fit your model, you need an initial population of susceptibles and of immunes also. So then we found that if you consider about 6% of the population susceptibles, in the case of the data of New York City for measles, then you could get this curve with the correct amplitude, like 8,000 more or less the peak. Okay, so but obviously this was got this out of the blue. So, I mean, 6%. Why 6%? You don't know. Okay, so there are reasons that you can try to calculate this. Maybe we'll comment this today. So. But now, remember that we have our long time plots. For measles, this is the one on the right part here. And you see that measles is a recurrent epidemic, okay? So you have it from time to time, right? So that, and there are other diseases that also fit into the scheme, yeah? Like influenza. Influenza is a classical case. They have a period of 1 year, okay? And so the point is, our SIR model cannot explain this. As it is written, it has no solution with recurrent epidemics. So one thing that Renato explained yesterday was that if your immunity wanes, you have a certain immune period, but you become susceptible again, then you had these periodic things, okay? But this is not true for measles. You don't lose the immunity. Immunity is most of the time lifelong. Okay? It can be people that have immune problems and so on, but as a good approximation, measles gives you lifelong immunity. You don't have people that have measles twice. And so that mechanism of waning immunity cannot explain this kind of thing. Although it has oscillations at the biological mechanism behind the oscillation that Renato told you about yesterday are not the ones that can explain the measles data. Okay? Now, that is so we have to look at what could be the reasons that we have the oscillations. And so we discussed this briefly yesterday. It's the fact that there are people that die and people that are born. Okay? And the people are born susceptibles. Therefore, there is an influx of susceptibles which can, from time to time, be large enough so to have an epidemic. Okay? So let's look at our SIR model, and let us consider, let us modify the model in such a way that we have birth and death. But we don't want to model the demographics of the population. So we want the population should be constant, still constant. I don't want to model the increase of the population because I'm mixing two effects, the epidemic dynamics and the population demographical dynamics. I want these things separate. Okay? And still it's a good approximation, usually that the population is constant. And then obviously you can modify this and take a small variation of the population, and then you can also build models and see how different they are and so on. But let's start with modeling a constant population, but with what we call vital dynamics. Vital dynamics is the fact that there are people that are born and people die. And the population is constant, so let me take a look at my... So we will have still dsdt, gidt, and drdt. And immunity of the recovered people will still be lifelong. Okay? So here, but this equation has to be modified from what we discussed yesterday, because people that are born susceptibles. Okay? They don't are born infectious or recovered. So there will be a birth time, and we will look at it in a moment. For the time being, this represents that there is an influx of people, in susceptible people, from the fact that there are people that are given birth. So, well, and then you have the usual thing, which is the dynamics of the infectious, susceptible encounters and so on, like yesterday. I don't want to repeat the discussion. But then I have also to model the death of people. But people die in all classes, right? In the first approximation here, okay? Obviously, if I had an age-structured model, I would have death rates depending on the age class and so on. Very much more complicated thing. Okay? But well, I will say that the death is modeled by a new parameter, which I call mu, times the population of that class, which is just saying that the death rate, if you think about this, for instance, this would be the rate at which population, at which susceptibles die per capita, per susceptible. And this term would be constant. So there's constant per capita death rate, okay? So, well, and then I have the same thing here for that we had yesterday, but also, there are people that will die here. From the mu? This is the same, these are the usual, same thing as yesterday. And I'm putting here only, I'm putting that all susceptibles may die, and that this death rate is constant per capita. Okay? Oh, because of the, okay, no, it's the same. Okay. So, and here I have the people that die, but also I have what we had yesterday, which was the gamma, which is the duration of, 1 over gamma is the duration of the disease. Yes? I will come to the B in a moment. Okay? The B obviously cannot be just a constant. Okay? It has to be somehow proportional to the total population. Okay? So the amount of people that are given birth is proportional to the total population. I'm not taking into account people the fact that there are ages that don't have birth and so on. Okay? So the B, we will come to the B in the next moment. So, and then I have for R, I get what I got yesterday. All of the people that are immune, which recovered, go to the recovered class. And these people also die. But this, I'm considering that the disease has no sizable effect about the death rate. Okay, this is not a model for disease virulence, for instance. I could also have mortality due to the disease. I would have to modify this. I'm not considering that. It's not a disease that kills you. Okay? So now, very beautiful. But, well, I have one more parameter, that is the mu, and we still have to discuss the B. So mu, 1 over mu, is the typical lifespan of people, okay? Which is much larger than the duration of the disease. That's why we didn't take it into account yesterday, right? So, but we still want the population to be constant. So I can sum everything here. I sum, let's go 1, equation 2, equation 3, and I can sum 1 plus 2 plus 3, and then I will get ddt on this side here, on the left hand. You will have S plus I plus R. Okay? But S plus I plus R is N. Okay? The total population. And when I sum this one with this one and this one, you see this one will cancel with that one, and this one here cancels with this one. Then we have only B minus mu S plus I plus R, which is N. So that's the variation of the population size. But we want the population to be constant. therefore it should not have zero derivative. And when you put this, this implies I will take B equal to mu n, which is also reasonable. Reasonable in the sense that the birth rate should depend on the total population. Yeah? The more people you have, more births you have. But and the coefficient here is would be the coefficient of the per capita birth rate, okay? And I'm taking it equal to the death rate in order to maintain the population constant and not study demographics here. I want only to study the epidemic dynamics. Okay, so that's our model. Good. Well, this model, we want to start to study it. First thing what we do in all models that we have is calculate the conditions for an epidemic to exist, which in mathematical language would be invasibility. No, it's not so much ecological language, is invasibility criteria. Yeah? So in ecology, we have very similar equations. And usually you have the case, many times you have the case where you have a population of a certain species, and then there's a new species that arrives. And you want to see if this other population will be able to establish, therefore, a small number of invaders. You want to know if they will increase. So it's very similar here, where the population are the humans, and we want to know that if the new species, in this case, would be the pathogen, will actually invade. Okay? In ecology, it's the rest of these things here is not the same. And I'm not saying that this is exactly like ecology, but there is a kind of analogy. So, and in order to know if the population will increase, I have only to look at the equation for dIdt. At time equal to 0, at the initial point of the invasion, will be beta, and S is supposed to be equal to N at the beginning, because everybody is susceptible at the beginning. So you have S times I, beta times I, minus mu times I, minus gamma times I. Oh, that's nice, because this is just I multiplied by beta minus gamma, minus mu, minus gamma. And now the condition for epidemic means that I have to have beta minus mu minus gamma equal to bigger than 0, okay? Which is the same thing to say that beta divided by mu plus gamma has to be bigger than 1. And this is our R0 in this case. Okay? Very similar to the SIR model, but instead of having only the gamma, you have now the gamma plus the mortality rate. Okay? So this is nice, but now we will have some very different things that will happen here. Okay? So we will now suppose that R0 is bigger than 1. So I want to study the epidemic. And now, remember yesterday that plot, SIR model. where I've put I over n here and S over n here. And here at 1 is the starting point of the epidemic when S is equal to 1. And over the course of the epidemic, you increase the number. If this plot I will explain again. So I have S and I have I. Now, I don't have the time here, okay? I don't have S in terms of the time and nor I in terms of time. You have just I in terms of S. Okay? But this, what happens over time is that we will move on this curve. This is sometimes called by physicists, it's called a trajectory in the phase space. And mathematician will probably call it an orbit. Okay? And so you will move with time going this way. That means that this projection on the I-axis increases and S decreases. And then you go down. At a certain point, you have the peak of I, which will be at this value. And then you decrease I, and S continues to decrease until you get I equal to 0 here. And I have the population of susceptibles that remains susceptible at the end. Okay? So I had many curves like that. Each curve was for a different R0. Okay? So this is a small R0, and for instance, if you had, for measles, you have a very big R0, like 18, and you get very close to 0, but it's not 0, it's not technically 0, but okay, it's a very small remaining population that is susceptible. So we had that. So now, what we have here, let me introduce the language of what is called dynamical systems. So we, many times we do, when we study dynamical systems, we want to study what is called the qualitative dynamics. What is qualitative dynamics? Qualitative dynamics is, I don't know the solution. I cannot solve my equation. They are not solvable. But maybe I don't want to solve them. Okay? Maybe I'm okay in just knowing the general aspects of the situations. For instance, yesterday we could actually, without solving the equation, we could calculate the total size of the epidemic, which is very important. Okay? And actually, we can also calculate the size of the peak of infected people. You can do this also. So you can do a lot of things without solving. And so qualitative dynamics is also about that. I want to know the qualitative solution. In many practical applications, you want to solve. Then you go to Renato's class and you understand how to solve numerically, which is an approximation. Okay? So, good. Now, and in this language of dynamical systems, when we have a situation where the population is constant, or the variables are constant, and if it's not populations, it's something else, when you have this, you say you have a fixed point. A fixed point is where all of these three derivatives are 0. Nothing changes. Well, one fixed point is obviously here. The total population is susceptible. There are no infected and no recovered. And it is a fixed point. If you don't have the introduction of infectious individuals, it will remain with a constant population of susceptibles. That's it. Then you have other fixed points, which are these ones here. For each R0, you have one other fixed point here, which is when S is equal to the remaining population, and I is 0, and R is something also, okay? And they are all constant. When you arrive here, you are constant. You don't increase, you don't decrease, you are constant. And so this is also a fixed point. But the thing about fixed points is that you want to know if the fixed points are stable. And what is stable? Stable is like that. Given a fixed point, I want to know if I perturb this value. If I have, if I perturb this value, say instead of having S equal to N and I 0 and R 0, I'm say, well, let's say S is equal to N minus something, and this something is the same as the number of infected, but that is the case when you have the arrival of an infection, a pathogen in a population that's susceptible. And our question is, will this small perturbation from the value of the fixed point increase in time and drift away from the fixed point, or will it just return to the fixed point? Okay? So, look at here. This is a fixed point. Now, say that instead of having S over N equal to 1, it is like 0.99. And then I say, well, then I over N will not be, because the total population has to be N. So this will be 0.01. Okay? And the recovered are 0. So there's small perturbations in practice. And then your question is, if I start with these conditions, over the time, will I go back to S over N equal to 1? Or will I go completely away from it? Okay? So that's the notion of stability and without doing the real calculation. Okay? So stability against small perturbation. And here, the stability of the point S over N equal to 1 depends on R0. If R0 is smaller than 1, you have no epidemic. This means that I introduce a number of infected people, and they just won't spread. They won't increase the number of infected. Then you go back to S equal to N. Okay? But if R0 is bigger than 1, then the fixed point is unstable, because I introduce a small perturbation of the totally susceptible population. I introduce some very small amount of infectious people, and this will increase over time. It won't go back to S equal to N. It will spread, and we have an epidemic. Therefore, this fixed point here we have always R0 bigger than 1, because otherwise you don't have any dynamics. This fixed point is unstable. And the other point here is when S is equal to something and I is equal to 0, it's also a fixed point, but this fixed point is stable. Once you end the epidemic, then if you perturb that, if you have the end of the epidemic, and then you put some small amount of infectious people, this will not spread anymore. So this fixed point here is stable. Therefore, we have two fixed points. One is unstable, and one is stable, assuming R0 bigger than 1. Here I have a lot of them, but each curve is a different R0. Therefore, for given R0, we have only two fixed points, one stable and the other unstable. Now, this, going back to our previous calculation, R0 for the vital dynamics SIR model with vital dynamics is this. And that's actually the condition for the stability of the disease-free system. Disease-free is when you have I equal to 0. Okay? If I is equal to 0, and I have an equilibrium, say S equal to N, all the rest is 0. That's a fixed point. And this fixed point will be unstable if this guy is bigger than 1, which means I have an epidemic. Otherwise, I don't have. So you can rephrase mathematically this as saying that this the condition of stability of the disease-free equilibrium. Okay? So now I want, okay, this is one thing. And now I want to know, well, do I have another fixed point? And now comes a big difference with the SIR without vital dynamics, because we have another fixed point which is not given by I equal to 0. So if I want to find this fixed point, I have to take ds dt equal to 0, di dt equal to 0, and dr dt equal to 0. But again, this here is not very important, because r is not here, okay? So actually you have a system of 2 equations. And the number of recovered can be obtained if you solve only this 2-dimensional system. So, but now the SDT equal to 0 is okay. Let me modify this already and put this equal to mu times n. Remember, that was our thing here. And now I can find this fixed point. And no, I don't want to do this. I want to do the I equal to. So analogous to the previous thing. Then I have here at the very beginning, not at the very beginning, sorry. I have, if this is equal to 0, I have beta. So I will write S star and I star. Why do I put a star? Because now I want to find the values of S and I such that the population, that the dynamics of susceptibles and infectious individuals does not change. It goes to a fixed point. So it goes to a fixed point, therefore this is not anymore a function, it's a number. Okay? So then you will have this minus mu I minus gamma minus mu I. This is equal to 0. And now I cancel the I here, and I get beta times S star over n is equal to mu plus gamma. Okay, I put this on this side. The I has been cancelled. Therefore, I have the value of S over n is equal to mu plus gamma divided by beta, which happens to be the inverse of R0. So you have a population which has this value. Now I need to know also the value of I star, the value of the population of infected individuals at equilibrium. So I look at ds dt equal to 0. Okay. But I assume that S over N is 1 over R0. So this will give you here mu N minus mu S. I begin with this one, then this one, but now S is equal 1 over R0. Then you have minus mu divided by R0. And the last term is minus beta. But S over N is 1 over R0 times I star. Error. S over here, this is S. And I wrote this, but there is an N here, because it's S over N. Okay? So what is this? This is an equation for I star. Okay? It's an algebraic equation. I can isolate I, and I can get I star over N will be, from this equation, you put this on this side, and then you go back and forth, and we will get mu over beta I0 minus 1. So this is what have we actually found here. We found that this model has two fixed points. We could analyze the stability of the fixed points. I won't do this. But I can tell you that if you do this, you will get that this fixed point with S star equal to this and I star equal to this is a stable fixed point. And while with R0 bigger than 1. And that disease-free state is unstable if R0 is bigger than 1. So what I found is that over the course of the epidemic, this epidemic will not burn out. It will go to a stable state where S and I are both different from 0. And this is an endemic case. So vital dynamics can lead you to an endemic situation. And the reason is that you are replenishing the pool of susceptibles by the newborns that come from here. Therefore, you accumulate newborns that are not immune, and then you can have, again, epidemic. So, and this leads you to a situation where you go to an equilibrium, which is, in this equilibrium is without, it's not with I equal to 0. And this is all of this is very consistent, yes? Because look at it. If mu is 0, I go back to the yesterday model, right? And we knew that at the end, we would have a population with I equal to 0, which was this point here. And now, if mu is different from 0, I don't go to this point anymore. I will have a different faceplate. I will draw it in a moment. So this is, now, I say, I know that a totally susceptible population will be, so to say, invaded, and I will have an epidemic if R0 is bigger than 1. And at the end, I will go to an endemic state. But I also interested in knowing what happens between these two times, between 0 and infinity. How is the dynamics? Because, you know, the number of infected could increase steadily and go to an equilibrium. So, possibilities. For I over n. In time, one thing is, well, it has to increase at the beginning because we are supposing r 0 bigger than 1. So it could go to just some fixed point here. But it could also make something different. It could grow and decrease, grow and decrease, and oscillate until it gets to the fixed point. This is, when you have this kind of situation, you say that you have the variable of infected people overshoots. So it will go to an equilibrium, but first it goes above, and then below, and then goes on. So this is similar to what we had yesterday with Renato. He showed us a system where this was not the system because it was a waning immunity system. But it also has this kind of solutions. So this here does not happen in this moment. What happens is this. How do I know this? I won't do the calculation because I need some linear algebra. Not so. Yeah? So how do I know it? Is if you do if I do the fixed point analysis in a more mathematical correct way, I will come to the fact that the population at the stability of the fixed point will have something that would be like near the fixed point e to some lambda time, and lambda would be something which is a negative value plus an imaginary part. Okay? And when I have this, this would be not a decaying, it's a decaying function, but it oscillates. Okay? So, if you are not very mathematical minded and so on, just instead of trying to understand this out of nothing, just please believe in me. Yes. Yeah. Okay. So so we can have oscillations. Good. Now back to New York City. Oscillations, long time. Yeah. What's the problem with this? The oscillations do not decay. Yes? Do not decay. And our oscillations decay. So I'm one step from the good models. I still need something else. Right? So, I won't do these calculations because that will go exactly in the same way that Renato's class yesterday about the case where we had waning immunity, but we had also seasonality. Right? In the seasonality, but this was meant to be a model for influenza. And what he showed you is that if you have an external forcing from, and the external forcing in that case was beta, had to be some beta 0 plus beta 1 sinus of some frequency of time. Okay? I don't think he has written this, yes? Maybe not. But that I didn't pay attention to the class correctly. but the idea is that you have a transmission rate that depends on the seasons. Okay? And this is typical of influenza. This is very well known. But this also can happen with measles. And you can obtain sustained, non-decaying, non-damped oscillations if you suppose that you have external environmental forcing, if you want. Okay? For the case of influenza, yesterday, we had something which was magic, because remember the discussion about resonances. Okay, that was a little bit more abstract. But you have, in this system, like in this one, we have a natural oscillation here, which will depend on the parameters of my model, okay? And you have a new oscillation here, which is seasons. So we have two frequencies. And what Renato explained is if these frequencies were the same, then you have the maximum amplitude oscillations. And something like this will also happen here. You have resonances and so on. What I don't remember if Renato told you, it is for influenza, there's something which is really weird, I mean, very wide thing. That the period of oscillations, which is intrinsic, because it's here in this model, or in the model of Renato for influenza. So yeah, I'm not talking measles now. Influenza, like yesterday, also has these oscillations. And these oscillations have a period. And it happens that the combination of constants in the waning immunity model is such that this is very close to 1 year, which is also the period of the seasons. The seasons repeat every year. So it seems to be a wild coincidence that this is so. So, but we don't believe in coincidences, yes? No? At least not at first sight. I mean, we only believe in coincidences when we can't find a better explanation. But then there you can really go to speculations in the case of influenza, that why does it happen that the period of oscillations due to wane immunity is the same period of the seasons, okay? This is not given a priori, okay? So, well, there's a famous phrase that every biologist has learned probably in Biology 101, which is nothing in biology makes sense except in view of evolution, right? So this is a phrase from very famous geneticist and ecologist also, which is Theodosius Dobzhansky, which, by the way, when it came to Brazil, it's one of the initiator of the biology department of the University of São Paulo. Not as initiator, but really gave the modern view of genetics in Brazil. So, then you could try to argue that somehow the values of those parameters here they are not arbitrary. They have to come from somewhere. Okay? Why is the waning immunity, for instance, from yesterday, why is the value of the constant that represents the phenomenon that value, and why is beta has a certain value, why gamma has a certain value? It could be an evolution of the disease, of the pathogen. Could be over a long time. It could be an adaptation. Because influenza is very old. It is at least 7,000 years. 7,000 years. So from the very beginning of what you could call history, but I mean, it could be older, but Well, with genetics, you can also get to nowadays an idea. So it's like this. So maybe it's a speculation. You cannot prove this. Why is the parameter? Why do parameters have their precise values and not other values? Okay? So in order to look at this, at the point we are here, we can only speculate. Now what? Now I want to know, instead of this plot, what kind of plot do I have in this case with vital dynamics? It cannot be this, because all fixed points here have I equal to 0. This one is not equal to 0. So therefore, if you make the same plot and you take the solutions, which you can obtain numerically. Yesterday I could obtain by hand, by doing calculations. Not anymore, okay? Not anymore. Because I relied heavily on dividing one equation by the others, but this equation here had only this one. And now you would have a division with many terms. It's not practical. Yeah. But you can solve the equation numerically, and you take at initial instant, it will be here, okay? Populations all susceptible, and then you take your solutions, S and I, you calculate it for every moment of time, and you plot is this here and this diagram, okay? So you will have something which increases, but you know, it has to go to a fixed point. So this is S star over N, and I star over N, okay? That will do something like that. It will increase, overshoot, undershoot, and go spiraling. It's a spiral, okay? So this is, S is initially only decreasing, and I is increasing, but at a certain point, I have a peak, then I go down, but as people are born, S can again increase, and then I go on and so on and so on. So I go to a spiral. So this is the phase diagram for the vital dynamics SIR model. Okay? So nice. So you see, so then we introduced different model, but it's very similar to the other one, but just putting the fact that people die and people are given birth modifies everything. Okay? So you have the spiral, you have the oscillations, you have an endemic state, very different qualitatively from what we had yesterday. Right? Well, okay. So this is an example of models of a modified model. Now, I have still 20 minutes. And what I will do is, I will now show you, but really show you, but not analyze, many models. Models galore. Okay? So, what would be a model where you don't have immunity? Case of gonorrhea, for instance. A model that would have no immunity is a model where you have a susceptible population that gets infected. Okay? And I put this here. Okay? But once the infection is over on the person after the duration of the infection, you don't get to R model. You get back to S. Therefore, you have a this is a SIS model. This is a very simple model, actually. We can even write it, okay, because this is really simple. So you have the usual term here. But instead of this guy going to the R, it goes back to S. And that's the model. Huh? So, this will lead you to fixed point dynamics. And actually can have all the population now being affected. It's possible. Okay? Because you don't have any immunity, you can infect everybody. Okay? So, then what else? And we have, so every different model corresponds to some different biological mechanism that you are taking into account. And the other one would be the model with waning immunity. Which would be an SIR model with, so this is like, would be like this. You get immune, but you go back to S. Similar to this one, but one more compartment. And it would be like an SI model, SIR model. But there's a rate and there's a flow of recovered people that lose immunity and become susceptible again. Therefore, I would have to put minus. Let us take lambda as a constant related to the duration of your immunity. 1 over lambda will be the typical duration of your immunity. Yeah? And this flows in here. This is the system that you studied numerically yesterday. Waning immunity, and the solutions are a fixed point, endemic state with oscillations. So the transient dynamics, until you get to the fixed point, is. Then another one, which is, this is used for respiratory infections like COVID or even influenza and so on, to give more realism to the fact that the person can be infected and has a latent period. Okay? So, yeah. Yes, you're right, and this is wrong. Okay, I changed signs. Waning immunity, so then you have a latent period. With it will be called SEIR model. You will have S. You will have E about, it's usually called exposed. Then you get infected. And this is the way you get infected. It's the contact of S with I. And then you get recovered. Okay? So now we will have 4 equations, okay? And you get worried, oh, the number of equations is increasing, so it will be difficult to study and so on. But this model is not so difficult. I will give you, probably in the next class, I will talk a lot about calculating the R0, the reproductive number, and in more general situations. And I will use this as an example. Okay? But here, this is modeling the fact that you get infected, you are not infectious, there's some time, and then you get infectious because it's a natural process. If it's a viral, it's the viral load that increases to a point that you really are infectious. Okay? Now, there could be a variation of this model, which would be the fact that you get exposed and you have a first phase where you don't have symptoms, but you are already infectious. Okay? Then I would have a new possibility of being infected, which would be E and S being in contact, generating a new one, and then the rest is the same. Okay? So this would be a different model. It's also SEIR model, but the two model that you have an asymptomatic phase before you get the symptoms. Why? But then you could say, okay, but, well, couldn't you just stay with the SIR model in that case, but now I is the total number of infectious people, okay? Asymptomatic and symptomatic. Yes, but this does not connect well to data because you don't have data about asymptomatic eyes because they didn't go to the doctor because they have nothing, okay? So in order to connect to data, you want the eye to be really the symptomatic eyes, okay? So that's why you use SEIR models. And this is very common for respiratory diseases, but it's also, I mean, for other diseases. It would be the case of HIV/AIDS without this guy because you don't recover, with a very long period of asymptomatic cases in person, but actually models for AIDS, HIV/AIDS are very different. Okay, that doesn't come now into the discussion. And then you can also have things like carrier states. I didn't write the equations here because once you get more or less acquainted with that way of doing, it's always the same. It's a beta SI. The only thing that you have to take into account is now you have an E and so on. But it's always fluxes from one compartment to the other due to two processes. One is the natural process of going to the removed because you are not anymore sick, and then there's the process of infection, which are always, almost always, this SI beta term. Okay, so once you give the diagram, you can do the model in less than 5 minutes. The point about modeling is not that the difficulty to write down the equations. The difficulty is to know which diagram adapts to your actual situation. Yes, That's more difficult. Yeah? So carrier state would be something like that. I have S, and I have I. Same process. But once I get infected, I have two possibilities. I can get recovered, but I can be a carrier. And I can be a carrier which can infect people. And usually with much lower infectivity. Okay? This is the case, for instance, for hepatitis B. And this is also a case, but a much more complicated model for malaria. Malaria has the pathogen has two main variants, which is called the falciparum or vivax. Falciparum, Plasmodium falciparum is the main malaria pathogen in Africa, and this is deadly. It's very important. In Brazil, we still have remaining falciparum, like at the borders with the Guianas places and so on. But this represents less than 5% of malaria cases in Brazil, because most of the cases are due to malaria vivax, which is less lethal. Mortality is low, but it has a carrier state. It stays you, and you can become infectious, and you can become sick again over years later, and then you can also infect other people, and other mosquitoes and so on. There's the vector. But so that's a case where carrier states are important, and this is important for malaria. Yeah, maybe, papillomavirus, I think so. Yeah, we can find more examples probably. Okay. And then, let us consider how would it be a model where you have more structures. Now, last model of the day. And Renato will talk about this, and so I want to talk before him. Right? But this is when you have another kinds of compartments. Many mathematical models, many diseases, they are different depending on, for instance, for your age, for instance. Okay? So you could have a model where instead of having my usual, let's say SI for simplicity, but this is because this is simple. You could have SI for S for young people, for older people. You have age classes. The same for I. And then you would say my parameters, you will have a beta for the young people and for the old people. Maybe they are different. The recovery time may be different also. It may depend on age. Therefore, you will have to age-structured model. For COVID, we actually had me, Renato, and my whole group and so on, we were working with a model inspired by model from people that we know in Oxford, which had, I think, kind of 18 age classes. 18. And even another model that we worked for COVID that was meant to describe the epidemics of the gamma variant in Manaus, we had 3 age classes. So the most simple thing. We had the young people, then you had intermediate people, and then you have older people. And so we had 3 clades. So instead of having only one S, we have S1, S2, S3. And this is also, there's also structured models when you have risk heterogeneities. There are people that are at a higher risk and people that are at a lower risk. So this is the case. Let me write this here. Would be an S, say high, that would go to this one, and then you can get here, and you get back, so it's an SIS model. But then you have also the low risks, which give you another class. You have the same thing here. You can get infected here. But you can also get infected with a contact of people of high risk with people of low risk. So this guy may infect this guy. So you have a new thing here that you can also have this. And then you can also have this. A high-risk person in contact with a low-risk person can infect the low-risk person. Right? So you have this system of coupled things. And just to end, let us, I don't want to really write down the whole system, but let me just write down how would be the equations for the infected guys. High, low. Okay, because you will have now a class of high and low, and another class of low risk. But this would lead you to have something like S hash divided times I hash divided by n with some beta. Then I would also have the high risks in contact with the low risks. Right? And then you can also have minus mu I high risk going back to S. Okay? But here, I have a beta, and I have another beta here. So I will call this beta index ash ash and beta index ash ash L. Now I have 2 betas. Because probably the lower risk, I mean, probably not. The lower risks people, maybe they have a different infectivity than the high risk people. Okay? And then you would hear, but for this it is similar. You have the contacts of susceptible and infected, both being of the same class, and then you have the interclass thing, which would be like that. Mu high, mu L, I, L. I don't want to analyze the system because Renato will do it. But the point is that you see, you now have 4 betas here. And you could even make something like this, write a matrix. A matrix of infectivities. Okay? Now you have 4 terms. This is high risk, susceptible with high risk, infectious. This is high risk, susceptible, low risk infectious. And now, remember that the discussion about beta, the infectivity parameter, depends also of the number of contacts. More contacts, more infections. So beta was not only biological, it was connected to having more contacts. Now, in order to study this beta matrix here, I have to have an idea about the number of contacts inside the same class between high-risk people, but also cross over different classes. The number of contacts of high people with low people and with low-risk people, and then also the low risk with low risk. So you need to have what? An idea about how the number of contacts, how the infectivity depends on the contact rates, and the contact rates form what will be, as usually called, the contact matrix. And this contact matrix is very difficult to study, because this is not anymore a problem of epidemiology, it's a problem of demography. Okay? For instance, this instead of having high risk, low risk, it could be young and old. Okay? So how is it that older people have more contact with other older people or with younger people? You know, it depends on the society, but there's a lot of things. And having this is a problem in demography which is very difficult to solve. I mean, it is not only difficult to solve, it's difficult to obtain this, because you would have to screen your population. Well, you have to screen your population, you have to go in field work and try to establish the contacts between the classes that you are considering, for age classes, risk classes, or whatever. And that is very expensive. Okay? Trying to make interviews with lots of people, thousands and thousands of people. Actually, I know a person that tried to obtain money for that, at the professor of the political science at USP, and she works with health policies and so on. And she tried to obtain money for that, but she couldn't get it. It was too much. So when you have this, what do you do? Well, there are people that have actually done this work, but unfortunately not in Brazil. And the best data is from England and from UK. And what did we do when we worked with COVID? We have also age classes, and not only we, all the world. A model for COVID without the age classes is not realistic. And so there are extrapolations from the data from UK, taking into account the age pyramid, the age distribution of different societies, and inferring the contact rates at outside for other countries that are not the UK, which is, oh my God, is this correct or not? Well, you cannot know, because you don't have the money to do the field work, right? So this is a critical point, and what people do is they have these contact matrices which have a lot of theory inside. And it's not direct measurement. Okay? So that's all for today. So tomorrow I don't teach you. Tomorrow you have 2 classes with Marcelo Gomes, and about that will be also wild things. Data for disease surveillance. Very different from this. No equations, lots of data. Weird. Okay? But this is really real world thing. Okay? So how do people actually, he will probably talk about respiratory diseases because he works with that. And how people that actually work at public health institutions. Marcelo Gomes is a professor as a researcher at Fiocruz in Rio de Janeiro. So how do they do the real work? It's nice. Okay, coffee break.